Welcome to Lecture 10A. In this case, we're interested in double integrals over general regions. The material for this lecture comes from section 16.2 of the text. The objectives of this lecture are to develop the tools for computing double integrals in a Cartesian coordinate system with integration limits on the inner integral containing functions, not constants, functions. The concepts and visualization skills that you acquire from this lecture include the Riemann sum in 2D, again just sort of a reiteration of what we did in the previous lecture, the relationship between integration limits, and two curved lines and two straight lines bounding the two regions. So now the region is no longer described by something that's of rectangular origin, but actually has some curvature to it in principle. And secondly, the changing order. The last item is changing the order of integration. There's a general note that it's important that you learn how to sketch the regions, since this will assist you in determining the bounds on the integral. So can't emphasize it more. You really need to draw pictures to help you understand integration. All right, as usual, the second slide is a summary of the different slides within this lecture, so I'll just move on. All right, so let's look at a class of bounds. So these would be the inner bounds, which are between two functions. And so I've got basically on the leftmost side a column where I look at geometrically how these different pictures differ. So for the first case, top left-hand corner, you basically see a black curve and a red curve, one labeled y equals h of x, the other y equals g of x. And there are no intersection points between the upper curve and the lower curve. In other words, the integration along x is between a and b. The second picture down basically has a single intersection point at x equals a. Now, they may not stipulate what x equals a is, but you'll be given the curves so that you can determine where the intersection point occurs, which means you can determine what the value of a ought to be. On the other side, b is still b. The third case is where you have two intersection points. Both on the left and right, you have an intersection. So in this case, you would have to equate y equals hx with y equals gx to figure out the solutions for the intersection points, and those would become your x equal a and x equal b value. So what you see on the left are pictures where you're going to integrate first with respect to y, then followed with respect to x. On the other hand, if you look at the rightmost figures in column form, you'll notice that if I plot y versus x, the functions basically, if you draw a line that goes vertically, there are two values for a given value of x. Well, we can't integrate because it has to be a function with a single mapping between x and y. However, if we turn the figure on its side, that is, rotate the picture counterclockwise by 90 degrees, that means x is pointing up and y is pointing to your left, then of course there are no issues. So then x equals h of y would be the upper surface, and x equals g of y would be the lower surface. In that case, of course, the integration order would change. We'd integrate with respect to x first, followed by integration with respect to y. And similar, you have another case where you have a single intersection point and two intersection points. Again, all you have to do is rotate those two figures counterclockwise by 9 degrees so that the y-axis is pointing to your left. And then you end up with pictures that look identical to the case where we talked about integration with respect to y followed by the integration with respect to x. So this type of picture will help you decide what order of integration you need to consider when you basically start working on a problem. All right, so now let's go through the process as we did before, the discretization of the region. Well, now basically we have two surfaces. We have a yellow line, which is the upper surface. The reddish line or purple line is the lower surface. And the bounds on x in this case will be the two red lines that you see. In this case, most likely they wouldn't be given. They'd be giving you the curves, and you'd have to figure out what the intersection points are to establish the lower limit on x and the upper limit on x. So the difference between this class of problem and the one we discussed in the last lecture is that now that the bounds, the inner bounds, are curved lines. In principle, maximum of 2 curved lines, but at least one of them would be a curved line. All right, you can look at a discretization, interactive simulation if you wish. You can get it at the URL, which is at the above, and you can play with a number of grids and things just to see how effectively you try to approximate the region. Clearly in this case, because you're dealing with a curve, you're going to find that the elements that you use to essentially tile the region may be incomplete. In other words, you only get fractional. But if you increase the number of discretization levels, then you're able to discretize the region more accurately. So that's the only difference, whereas in the previous case, because it's a rectangular, the squares would all fit within the rectangle. All right, so the Riemann sum hasn't changed. It's still the same expression. Difference being now that the region involves trying to fit little squares in a region which is no longer consisting of a rectangle. And so there's an approximation error now associated not just with the height, but also the region itself. But in the limit, effectively, the integral, this becomes an integral as before. So no changes, just that one small point that I wanted to make. Again, this is an interactive visualization that you can play with just to sort of watch what happens. And so now we can move on to look at the theorem 16.2, which is for double integrals over non-rectangular regions. So let R be a region bounded below and above by graphs of the continuous functions y of gx and h of y of x, respectively, and the lines x equals a and x equals b. If f is continuous in R, then the double integral fxy dA is the integral of a to b, integral g of x, h of x, fxy dy dx. So you'll notice here, and this is an important point to point, this y is a function of x. This x is always going to be between two constant values. The outer integral is always between two constant values. But this is y is a function of x, top and bottom. This function will always be smaller than this function. This constant will always be smaller than this constant. But keep that in mind when you set the problem up. On the other hand, we can have basically the other case where we basically iterate the integral. So in this case, let R be a region bound on the left and right by graphs of the continuous function x equals g of y and x equals h of y, respectively, and the lines y equals c and y equals d. Again, if f is continuous in R, then in this case, basically with the order of integration reversed, we now have this dx linking with this and this dy linking with this. So in this case, x is a function of y, x is a function of y. Again, this value should be larger than this, and this should be larger than this. So again, we go back to our notion of what do we mean in terms of geometric interpretation. Well, let's go here now. There's a difference. In this case, y is explicitly a function of x, so that is a line. Okay, there's no doubt about it, and this is a line. On the outer integral, we have x equals a, but again, y has not been defined, but because it's 2D, y is an element of R. So these two are vertical lines, and these two, in principle, are curved lines. Okay, maybe one is straight, it depends on the nature of the problem. But this is basically how you should interpret when we do a double integral. All right, let's go through an example. Again, this time just consider just a slicing method in the x direction. Now the difference here, you'll notice that the region, here's y, is h of x. This is the larger of the two, so it's the upper bound on the integral. This is y equals gx, which is the lower. It's the lower bound on the integral. Again, we have a of x, but in this case, a of x now accounts also for the fact that this distance is changing. In other words, it's not a constant value anymore. So if you look at the integral here, again, now you're integrating with respect to y, but substituting finally after integrating in terms of functions of x. So all of this eventually becomes some function of a of x. And so for a given value of x, you're looking at a slice like this. Change the value of x, you're looking at this one. And then at the back end, x equals b, you'd see this. X equals a would be the one that you see back here. This is an interactive simulation that you can play with just to visualize what we're doing as you sweep values x from A to B. All right, so now let's look at another example, determination of integration bounds for an example problem. So problem is stated as follows. Express the integral, double integral, 2x squared y, which is the function f of x y dA, as an iterated integral where r is the region bounded by the parabolas y equals 3x squared and y equals 16 minus x squared, and then evaluate the integral. So the first thing to do is to sketch these parabolas, which is what is shown on the left. So there's the parabola y equals 16 minus x squared and the parabola y equals 3x squared. So the region is basically contained in here. Now what's not shown here is the bounds on x. This is a perfect example. We have two intersection points. So to find the bounds on x, we need to equate these two functions, which is what we basically are doing down here. So inner integral upper bound is 16 minus x squared, and lower is y equals 3x squared. That we know right away. To determine the lower and upper limits of the outer integral, we need to determine the intersection point of the two curves. So if we equate this with this, we end up with this expression. If you solve it, this implies that x equals 4, and thus x equals plus or minus 2. So this is x minus 2, and this is x equals positive 2. All right, so now we can do the integration. Here are bounds, lower bound, upper bound for the integral with respect to y, lower bound, upper bound with the integral with respect to x. So everything here with respect to y is a of x. Ax is shown here. And so the rest is doing the integration, right? And if you work this through, this is just mechanics. You just have to do the integration, end up with an answer of roughly 663.2. Just remember that when you integrate with respect to y, x is held constant, okay? Now, the other thing is to figure out, well, what are we doing here? What are we actually physically calculating? So let's look at z. That's what's in here. Remember we mentioned that if this basically is greater than or equal to 0, then we're computing a volume under the curve where this would be the curve in the z direction. Well, you'll notice that 2x squared over y is always greater than or equal to 0. X squared is greater than 0 and y is greater than 0 because effectively it's not going below the x-axis. So in fact, we are computing a volume. Okay, so again, just to reiterate, you need to do a calculation of intersection points if the outer integral bounds are not explicitly stated. Here's a visualization, interactive visualization you can look at if you want to watch what's happening, particular integration taking place. So this basically would show it sweeping over and basically mapping out this region, which is integration over the region. All right, so a couple more things here. Let's choosing and changing the order of integration. This is another example. We're given the integral, double integral xy dA, right? And what we're basically going to do is compute both integrals and verify that the results are the same. So here are the basically what's being given in the problem. You're given that you've got a curve and you're given another curve. So we can integrate either first with respect to y followed by x or x followed by y. Now if you look at this, it falls into the class of problems where you have intersection point here and an intersection point here. Well, you can, just by looking at it, you can see that this value has to be 1. If this is basically y is a function of x, that's this one, y equals x 1/3 power, and y equals x squared. They're equal to each other when x equals 1. If you look the other way around, in other words, x being vertical and y being to your left, then x is a function of y, that's x equals square root of y, and x equals y cubed. Similarly, you'll find that in that case, y equals 1. All right, so the limits are clear. If you're doing dy dx, then this is the upper, this is the upper, and this is the lower. Upper, lower. 1, 0, 1, 0. So we just go through the process of integrating. You integrate with respect to y holding x constant, and then lastly you integrate with respect to x, and you get 5/48. If we reverse the order, that is dx followed dy, then this has to be a function of y. x has to be a function of y, which means that we're now looking at this being the upper one. Why? Because it's larger in the x value. And this basically being the lower one, because it's lower than this one if you look at in terms of the x direction. In terms of the range on y, 0 to 1. So 0 to 1 there. And so if you compute this, you'll also get 5 over 48. So the choice of integration order depends on which is the easiest to perform. In this particular example, either one would have been suitable choice, but it's not always the case. And this is just an interactive version of what I've just shown previously. You can look at it, maybe give you some additional insights into the nature of the problem. So that concludes Lecture 10A. Thank you for listening.